Now we move on to traffic analysis of highway bottlenecks. So the most severe congestion problems occur at highway bottlenecks. So highway bottlenecks actually is defined as a portion of a highway with a lower capacity than the incoming section of highway. So actually the result of the reduction in capacity can originate actually from the number of sources, including decrease in the number of highway lanes and reduced shoulder width, which tend to cause drivers to slow and thus effectively reduce highway capacity. So there are two general types of traffic bottlenecks: those that are reoccurring and those that are incident induced. So recurring bottleneck exists in the highway itself, limit capacity. For example, physical reduction in the number of lanes. So that is an illustration for a recurring bottlenecks. However, traffic congestion at such bottleneck results from recurring traffic flow that exceed the vehicle capacity of the highway in the bottleneck area. However, we have what we call the other one, incident-induced bottlenecks. So this is actually the result of vehicle breakdown or accident that effectively reduced highway capacity by restricting the through movement of traffic. So for our example, so we're going to have here an example problem. An incident occurs on freeway that has a capacity in the northbound direction before the incident of 4,000 vehicle per hour and a constant flow of 2,900 vehicle per hour during the morning commute. No adjustment to traffic flow result from the incident. At 8 a.m., a traffic accident closes the freeway to all traffic. At 8:12 a.m., the freeway is partially opened with a capacity of 2,000 vehicle per hour. Finally, the wreckage is removed and the freeway is restored to full capacity, which is 4,000 vehicle per hour at 8:31 a.m. Assume DD1 queuing to determine time of queue dissipation, longest queue length, total delay, average delay per vehicle, and longest wait of any vehicle. So for this one, we have to make use of mu, be the full capacity departure rate, and mu sub r be the partial capacity departure rate. So if we try to have a common unit for our arrival and departure rate, so we can have a vehicle per minute. So we can have here our mu. We have to take note that our mu, which is the full capacity departure rate, which is 4,000 vehicle per hour. So as the wreckage was removed, so the freeway was restored, so it has a full capacity of 4,000 vehicle per hour. So our mu will be 4,000 over 60, so we get here a value of 66.67 vehicle per minute. Then for mu sub r, that is the partial capacity departure rate. So during the incident, the freeway closes. The freeway rather was partially opened, so it has a capacity of 2,000 vehicle per hour. So if we try to convert this one to minutes, so divide to 60, so we get a 33.33 vehicle per minute. And for our lambda, which is our average arrival rate, we have the average arrival rate, which is 2,900 vehicle per hour. Convert this one, so we have here divide to 60, so we get a value of 48.33 vehicle per minute. So which means that if we're going to have here the arrival rate, which is constant over the entire period time, and the total number of vehicle is equal to lambda times t. So we can have our t, that is the number of minutes after 8 o'clock a.m. So t refers to the number of minutes after 8 o'clock a.m. So therefore, if we're going to have the total number of the departing vehicles, so before at 8 o'clock, before 8:12, so which means that before 8:12, so there was no the freeway because of the accident because of the accident that occurred, the the freeway closes because of the accident. So at 8 o'clock, the freeway closes. That is 8 o'clock to 8:12. So the freeway was closed, and therefore there was no departing vehicle. So that is why you have here 0. Since there are no departing vehicle during the accident wherein the freeway was closed from uh, 8 o'clock to 8:12, so which means that we have here 0. So this is 40 is less than or equal to 12 minutes. So this is before 8:12. So after 8:12 a.m., the freeway was partially opened. So it was partially open. So therefore, the departing vehicle would have an equation. So the departing vehicle will be, of course, mu sub r refers to the partial capacity departure which occurred during 8:12 to 8:31, actually. From 8:12 to 8:31, because at 8:31 it was fully opened. So at 8:12 it was partially opened up to 8:31, so which means our t is greater than or equal to 12 but less than or equal to 31 minutes. So which means that our departing vehicles will be equivalent to mu sub r, which is the partial capacity departure, mu sub r times t minus 12. T minus 12 because this is, we're going to have here after t minus 12 because that was opened at 8:12. So we're going to have here t times t minus 12. So this will be the equation, mu sub r times t minus 12. So that is when t is less than or equal to 12 minutes, but less than or equal to 31 minutes. Or rather, this is t is greater than or equal to 12 minutes, but less than 31 minutes. So that is the equation, mu sub r, this is partially capacity departure, times t minus 12. Then after 8:31, so at 8:31, it was fully opened. The freeway was open, so there is a full capacity departure of vehicles. So the full capacity departure of vehicles when t is greater than or equal to 31 minutes. So because at 8:31 it was fully opened, so the capacity or the departing vehicles, so that will be equivalent to, so that is 633.33 plus mu times t minus 31. So this one is 833.33. That is the departing vehicle in between 8:12 and 8:31. So in between 8:12 and 8:31, so that will be 31 minus that will be equivalent to, so our time here is between 12 to 31 minutes. So that will be 31 in between. Our t here is between 12 minutes to 31 minutes. So which means on that is 19 minutes. In between 12 to 31 minutes, that is 19 minutes because 31 minus 12 is equal to 19. 19 times our partial, because that is that the departure here is partial from 12 minutes to, from 8:12 to 38:31, which is a partial departure. So partial departure is 33.33. There are 33.33 vehicles that departed of that particular time. So 33.33 times our 19, which is in between 8:12 to 31 minutes. So which means that is equal now to 633.33. So plus mu, this is now the full capacity because after 31 minutes at 8:31, there is now a full capacity. So mu times t minus 31. So we have now our equation. So if we're going to equate our departure rate to arrival rate, so we have here arrival rate is equal to departure rate. So arrival rate equal to departure rate. So lambda times t is the average arrival rate equal to our full capacity departure rate, so that we can solve for our t. So our t here, if we're trying to solve this from this equation, is equal to 78.16 minutes. So 78.16 minutes actually is that is from 8 o'clock. So 78.16, meaning to say you have here na 1 hour and 18 minutes. So which means that is after 1 hour and 18 minutes, the there was now dissipation. So meaning to say the Q dissipates at 1 hour and 18 minutes. So that 1 hour and 18 minutes, that is actually from 8 a.m. to 9 a.m. and 18 minutes. So which means the exact time that the Q dissipates is at 9:18 a.m. So we have here 9:18 a.m. So which means that the total number of vehicles and the total number of vehicles that arrive and departed is equivalent to our arrival rate is 48.33 multiplied to our t, which is 78.16. So the total number of vehicles that arrive and departed is equivalent to 3,777.5 vehicles. So that is the number of vehicles that arrived and departed at 9:18 a.m. So our average arrival rate and our departure rate can be graph. We can draw the diagram using as we have discussed, using the DD1 queuing diagram. So using the DD1 queuing diagram based on our discussion on the DD1 model, so we have to graph our same procedure as how we graph our arrival rate and our departure rate. So we have here our arrival curve and this is our departure curve. So you simply have to identify along y-axis again your time, and along y-axis the number of vehicles, so that you could have the arrival curve and your departure curve. And of course from this you could identify the point of intersection, wherein the point of intersection of the arrival curve and the departure curve, wherein actually that point of intersection is the point of Q dissipation. So which means all vehicles that arrive has already departed, and based on this example, it departed after 78 minutes. So which means 78.16 to be exact minutes, which is actually at 9 a.m. and 18 minutes. So it departed at 9:18 a.m. So all the 3,777.5 vehicles that arrived, they departed at 9, all of them, even to the last queue. Even to the last queue, the queue dissipated at 9:18 a.m. Based on the curve, the longest vertical distance, or which refers to the longest queue between that is the longest vertical distance between arrival and departure curve. So actually, if you're going to observe, it is the longest curve here is at 8:31 a.m. So at 8:31 a.m. it is now the time wherein there is the longest queue. So which means that if you're going to have the longest queue, Q max, that will be equivalent to lambda t minus, you simply have to subtract, minus the arrival rate minus the partially departed rate. So that is equivalent to 48.33. That is the average arrival rate times 31 minus, you have here, this was partial arrival departure rate is 33.33. So this one is between 31 and 12. So 31 minus 12 is equal to 19. So you get a value of 865 vehicles. Then you can compute for the total delay. You simply have to get the area in between the arrival curve and the departure curve, and that is now equivalent to 37,604.2 vehicle minute.